This lesson is going to focus on the natural base e, and it'll be two parts. In the first part, we'll practice simplifying and graphing, and also graphing transformations. And then in the second part, we'll look at some applications. So by the end of this lesson, you'll be able to define the natural base e and evaluate powers of e graphically and numerically. As we go through this, be thinking about, again, how exponential functions model real-world problems and their solutions. And we'll look at a couple different examples, including a different type of calculation for compound interest. And then also, how can I use exponential functions to calculate interest on an account compounded continuously? So the vocabulary that we'll be looking at is the natural base e, which is also called the Euler number, and also natural base exponential function. So first of all, we are using this expression, the quantity of 1 plus 1 over n raised to the nth power. And what you find is, as the powers of 10 get larger and larger, this number, when you evaluate the expression, gets closer and closer to 2.71828, etc. This is an irrational number. So it's never going to terminate, and it's never going to repeat. And this quantity here, this 2.71828, repeat or continuing, is the natural base, or the Euler number. So first of all, we can simplify this just like we would anything else using laws of exponents when you see it in a problem like this. Which means that if I had something like e to the 6th power times e to the 4th power, those are the same base. The base is e, so I can add the exponents. So in this case, I would just say e6 plus 4th power, or e to the 10th power. Similarly, when I have the same base, I can subtract exponents when I'm dividing 2. So the first thing I'll do is I'll say 8 divided by 2 is 4. And this will be e to the 4 minus 6th power. And if I simplify that, 4 minus 6 is negative 2. And I can rewrite that as 4 over e squared. And just like with laws of exponents, I have a power raised to a power. And so I can rewrite this by distributing this 3. So 4 to the 3rd power times e. And then I am going to multiply 2x times 3. 4 to the 3rd power is 64. So I have 64 times e raised to the 2x times 3 is 6x power. And that's just a quick look at simplifying expressions involving e. What we'll look at next are these natural base exponential functions, which really aren't that much different than what we've already been looking at with exponential functions. So it's a function that takes the form f of x is equal to a times e raised to an rx power. So if a is greater than 0 and r is greater than 0, then the function is an exponential growth function. But if a is still greater than 0 and r is less than 0, the function is an exponential decay function. So we'll look at a couple of different examples and then do some transformations. So the first thing that we want to do is just graph a basic e function. So we'll look at 2. We'll look at e to the x power and e to the negative x power. Now, it doesn't say it, but my r value in each of these would be a 1 and a negative 1. So we're looking at one example of exponential growth and one example of exponential decay. Now, I know that because, again, my a value here is 1 and my a value here is 1. So I know my y-intercept is going to be 0, 1. So I'll start out on the left here by graphing that y-intercept of 0, 1. And let's just plug 1 as an x value so we can get a second point out. So if I put in 1 for x and e to the 1st power, or just e, is 2.718, etc. So now I need to plot 1 and 1, 2, somewhere between 2 and 3. We'll call that 2.718. And I'm going to sketch in the rest of my graph. It should be getting closer and closer. Let me make that closer and closer to 0. It should be closer and closer to 0, but not touching 0. So that is our asymptote, the x-axis, or y equals 0. And I had those points of 1, 2.718, and also 0 and 1. So that's just what the function of y is equal to e to the x power would look like. And y equals e to the negative x power, I'll start out by still plotting that y-intercept of 0, 1. But now if I put 1 in for x, it would make it to the negative first power, and I would get out 0.368. So that's going to be less than 1/2. And to see what the other side is going to look like, I'll choose an x value of -2. And if I plug that into this equation, it's really like saying e to the second power, because e to the opposite of -2 would be e squared, e to the second power. And so if I do that, I get 7.39. So if I put in -2, I would go -1, 2, and then 1, 2, 3, 4, 5, 6, 7, right about there. So you can see how the decay would look with this graph. Next, we'll look at a couple of examples that are a little bit less basic. We'll get to a transformation, but first of all, let's look at this first one that says 3 times e raised to the 0.75 times x power. Just like with a normal exponential growth function or decay function, this 3 is our a value, and that means my y-intercept is going to be at 0, 3. So I'm going to erase what's on the graph currently, and then I'll put my y-intercept at 0, 3. And if I plug 1 into this function just to get a second point out, I will get 6.35. So about there. And sketching what the rest of it looks like. It should be approaching but not touching the x-axis, or y equals 0. So that is what that first function would look like. Now let's actually do a transformation. So in this second example, I have y is equal to e raised to the negative 0.5 times the quantity of x minus 4 plus 2. Just like last time when we did transformations, we'll go ahead and start out by graphing the parent function, and then we will translate the whole line. So the very first thing we want to do is we want to graph the function y is equal to e raised to the negative 0.5 x power. Alright, sorry if I'm repeating myself. I just got caught up in a conversation mid-video making. So we're going to now do the transformation of this function here. And so we want to start out by just plotting or graphing the function e to the negative 0.5 x power. So with this one, we're still going to have a y-intercept of 0, 1. This is a decay function, though. To really see how it's going to move, I want to pick a negative starting value for x. Otherwise, it's just going to be a slightly smaller value, and that's not incredibly helpful. So if I put in -3 for x into this function here, I'm going to get out 4.48. So I'm going to plot 1, 2, 3, 4, 4.48. And there's a rough sketch of what the parent function should look like. But I won't want the parent function. I want to do this one. So looking at this, and this -4 and then +2, what I want to do is move my entire line to the right 4 and up 2. So I'll start out with this point and go over 4 up 2. And then the other point that I plotted, I'll go over 1, 2, 3, 4 and up 2. And then my new asymptote should be the line x is equal to 2. So that's the same as the exponential growth functions, where this k value here is our asymptote. And this is the end of part 1, so you can pause if you want to, you can go ahead if you want to and finish it. In the next part, we will look at applications of these functions, so continuously compounded interest, and also looking at some data. So continuously compounded interest is exactly what it sounds like. We're still working with compound interest. So instead of, though, compounding the account, once a day or once a month or once a year, it's continuous. So the equation is A equals P times E to the RT power. A is the amount you've earned with interest, P is the principal, R is that interest rate again, and T is the time in years. So what we'll do is we'll calculate this example with continuously compounded interest, and we'll compare it to the example we did in the first section with compounding it daily. But first, let's look at this example. We deposited $900 in an account that pays 6% annual interest, compounded continuously, and we want to know what the balance is after 2 years. So if I use this formula, I'll have A is equal to $900 times E. And remember that 6% should be written as 6/100ths as a decimal times 2 years. And if I do this math, I end up with about $1,014.75. So how does this compare to an interest that is compounded daily on the same account? So this is just like in the last section. We were looking at interest that was compounded every day versus every month versus just once a year. And they were all close, but the more often that the interest was compounded, the higher the balance was in the account at the end. So if we're looking at this, this is daily. We're going back to that other formula, which was the principal times 1 plus the rate divided by the number of times it was compounded, raised to the n times t power. So in this case, that will be 900 times the quantity of 1 plus 6/100ths over 365 raised to the 2 times 365th power. And if I do the math here, I get something very close, which is $1,014.74. And again, you will have access to both of these formulas when you have to do this on the exam, so please don't bother memorizing them. You just have to know when you would use each one. All right, last we will look at an exponential model for data. So the speed in meters per second that an athlete can run can be modeled by this function. S is equal to 9.8 minus 9.8e raised to the negative 88/100ths times t power, where t is the time after the athlete's rushing off in seconds. So if we're looking for the athlete's initial speed, the starting point, that would just be 9.8 meters per second. And then let's evaluate this for 3 seconds after launching off, and we're going to round that to the nearest tenth of a meter per second. So looking at this formula, I would say S is equal to 9 and 8/10 minus 9 and 8/10 times e raised to the negative 88/100 times 3. And if I do that math, I get 9.1 seconds. In the next video, we're going to get into logarithms. And I want you to keep in mind questions like this, because in the next section, we're going to be looking at how you could solve for a different variable. So a variable that's not quite so obvious to just plug it into the formula. And there are no questions to answer for practice with this particular section.